Hey guys, so welcome back to your next lesson of catalyst concepts. Today we're going to start a new lesson and that is called classification of elements. Okay, so you have a brief idea about this. I think in one of the videos we spoke about periodic table and like some of the first few elements that are there. So today we're going to start the lesson which tells us about how this periodic table came about, this whole idea of classification, why it came. Okay, so back in around the 1600s, when people were just starting to define what is the meaning of this word element, there were not a lot of elements known, maybe around 13 elements only. Okay, but as time grew all the way over 1600, 17, 18, 1900, so by the time it was, I think, 1940s or so, we had 91 elements on our hand, most of them naturally occurring, right? Now, it's easy to remember 13 element names and properties, but it's not easy to remember 91 different names and properties, right? So there was an attempt by the scientists to actively look for any common properties or any common method by which to identify any of these elements or to segregate them. Okay, for example, if I give you a couple of like a basket of mixed fruits, like different fruits, I just throw them in and give it to you. Say maybe an apple, maybe a kiwi, maybe a grape, maybe a chiku, a watermelon, right? So this is just a mix of different fruits. In a way, I can talk about them as different elements, right? If I give you this basket and ask you to just sort them, arrange them, you might come up with different things, right? One of you might want to put them according to size, saying, "Ki, I'll start with the smallest. I'll go with the grape. Then after that, I'll put the kiwis. Then I'll go with the chikus. Then I'll go with the apples, and then watermelon largest, however it may be." Some of you might say, let's go by the weight of it. Okay, how heavy it is. Starting from the lightest, go to the heaviest. Okay, start with the grape, then maybe the chiku, maybe the kiwi, then apple, and then finally watermelon. But all of this is very simple when there are very few of these. What if I give you like hundreds of fruits together, right? And I tell you to just put them. Then what? One thing that can happen is what we call as grouping, right? You can group them according to some common properties that they have. For example, I can say, let me group by color. I'll put all of the things with a similar color together. So maybe if I come to the color green, I'll say, okay, I'm going to put my grapes because that's something that is green. And then maybe I'll put my green apples. And then maybe I'll put my raw bananas, technically a fruit. So if you see, these are all grouped according to some property that they have in common, but within themselves also we arrange them in size, okay, smallest to largest. So it becomes easy for us to categorize and understand. So scientists are trying to do something similar with all of these 91 elements that they had and more that kept adding in the years after. So one of the first attempts at this was by a guy named Dobereiner. Okay, Dobereiner. Okay, so Dobereiner, what he observed was there are some chemicals or some elements, they have similar properties. Okay, elements with similar properties, similar in the sense they undertake the same type of reactions. Like they might be metals or they might be non-metals. In some sense, they'll have properties that are matching with each other. And one trend he noticed is that you can group them in a way according to their weights. Okay, group according to weights. But he was looking for something very specific. He said that in a group, what I can do, I can have three elements. Okay, three elements, and of these three, let's say element number one, element number two, element number three. Okay, all grouped by their weight. Okay, so this will be the lightest, this will be the heaviest. He said average of first and third elements weights. Okay, so average of weight of first and third elements will be equal to weight of second element. Okay, in speaking it's a little confusing, so I'm going to show you a small example. Okay, so there are three elements that are similar in properties: lithium, sodium, and potassium. Okay, so these are what we call as rare earth metals or alkali metals. They're all in group one and they have similar properties. So he said that the average weight of lithium and potassium will be the weight of sodium. Okay, so here I have a table. If you can see, lithium, sodium, potassium, okay, vertically, and their weights are also written. Over here we have decimal weights, but back then the weights were all round numbers. So lithium's weight was given as about 7, sodium's was 23, and the last one, which is 39.1, was taken just as 39. Okay, so if I take average of lithium and potassium, 7 plus 39 divided by 2. Okay, that is 46 by 2, which is 23, right? Which is exactly the same as my sodium's weight. So he said that these are called triads. Okay, triad. Tri means three, right? So he says these are all groups of three elements wherein the first and thirds elements averages will be equal to the weight of the second element. Okay, so this was his theory, and it did hold true for a specific set only. Okay, the problem with this was there were only three triads for which this worked. Okay, at one point of time there are only three triads. So here is one that we discussed: sodium, lithium, and potassium. There's another one: calcium, strontium, barium, chlorine, bromine, and iodine. Okay, it did not apply for all of the elements that they knew at the time. Okay, so one problem with this is did not apply to all elements, although it is, yeah, apply to all. That is one problem. Another thing is that as time kept going further, since like I said, they had only round numbers for weights, they didn't exactly calculate the weight properly. But as time went, they were able to make all these decimal measurements also, and it did not properly hold for the average. Okay, so the average was not exactly as he had said. There was a little variation even in the weights that had come. Okay, so these are some of the limitations of this Dobereiner's triad model. Now, one another issue was that if the elements are like a bit too heavy, like for example, for really small elements with very lightweight, for really big elements with a lot of heavy weight, that did not apply at all. It used to go very wild, right? So there was only a very limited scope for this. So although this attempt had like a lot of flaws and problems, it was a good attempt at trying starting towards something. So this is like one of the first proper attempts at, we say, classifying elements. The attempts that followed were like a little, learned a little from this and then changed some things and tried out something else. So this is where I'll stop for today. So we have learned about something called Dobereiner's law of triads. Okay. In the next class, we're gonna go through the next attempt of classifying elements. We'll talk about that in the next class. If you have any questions, doubts, please post them in the comments below, and I'll see you again in the next class. Thank you.